Hi everyone, I'm Chen Pan. I'm a junior undergraduate student at University of Texas at Dallas. This presentation is based on the RU program I did here at UTD this 2024 summer. Today we'll be focused on how machine learning can significantly enhance the traditional fuzz testing technique used for vulnerability discovery in software testing. Introduction. As software and application become more complex, their code structure also become more intricate, increasing the potential for security vulnerabilities. Complex code is likely to contain hidden flaws that attackers can exploit, leading to data breach, system crashes, service disruption, and other security issues. Therefore, detect security threats and maintaining secure operation of software is a crucial task. Fuzz testing is also one of the effective methods for vulnerability discovery. By providing unconventional data input into the target program, fuzz testing attempts to trigger anomalies, thereby revealing potential vulnerabilities. However, traditional fuzzing techniques have several limitations, such as incomplete coverage and low automation level. This is where machine learning comes in, offering advanced data analysis and classification capabilities that can enhance fuzz testing significantly. Today, this presentation will be about ways machine learning can optimize various stages of fuzzing, the challenges faced, and the future prospect of this integration. Overview of fuzz testing. Fuzz testing, also known as fuzzing, is a software testing technique used to discover security flaws and bugs in software by providing random unexpected inputs. The primary objective of this fuzzing is to test the robustness of programs and identify any potential vulnerabilities that could be exploited by attackers. The concept of fuzzing was first introduced by Professor Barton Miller in 1990. He designed a tool called Fuzz to test the robustness of Unix utilities by providing them with random input data. Since then, fuzz testing has evolved significantly with the development of black box, white box, and gray box fuzzers. Despite its effectiveness, traditional fuzzing method faces several challenges, including complete coverage, low automation level, and insufficient test cases. This limitation often resulted in lower success rate in discovering critical vulnerabilities, making it necessary to explore advanced techniques like machine learning to enhance fuzz testing. Challenges in traditional fuzzing. One of the primary challenges is incomplete logic coverage. Traditional fuzzers often fail to explore all possible execution paths within a program, leaving some flaws undiscovered. This is particularly problematic in complex software systems where the number of possibility execution paths can be enormous. Another is low-level automation. Traditional fuzzing requires substantial manual effort to configure and execute tests, as well to analyze the result. This manual intervention not only increases the time and cost associated with the fuzz testing, but also introduces the potential for human error. Lastly, traditional fuzzing technique often suffer from insufficient test cases. The quality and diversity of the test cases are crucial for effective fuzzing. However, generating a large number of high-quality test cases manually is both time-consuming and challenging. This limitation necessitates the exploration of advanced techniques such as machine learning to enhance the efficiency and effectiveness of fuzz testing. Machine learning, with its exceptional capabilities in data analysis, pattern recognizing, and classification prediction, represent a promising approach to enhance fuzz testing. By integrating machine learning techniques, we can address many of the limitations of traditional fuzzing methods. For instance, machine learning algorithms can be used to automate the generation of test cases, significantly reduce the manual effort required. They can also improve the coverage of fuzzing by exploring more execution paths within a target program. Additionally, machine learning can enhance the effectiveness of fuzzing by prioritizing the selection of test input that are more likely to trigger vulnerabilities. The integration of machine learning with test fuzzing can be applied across various stages like fuzzing processing, include preprocessing, test case generation, input selection, and result analysis. Each of these stages can benefit from advanced capability of machine learning, leading to more effective and efficient testing. Workflow of fuzzing. To understand how machine learning can enhance fuzzing, let's look at the workflow of fuzzing and how each stage can benefit from machine learning techniques. The workflow of fuzzing can be divided into four main stages: pre-processing, test case generation, input selection, and result analysis. The pre-processing stage, relevant information about target program is collected, and the strategy for fuzzing is specified. Machine learning algorithm can be used to analyze and predict this information, enhancing the effectiveness of program analysis technique combined with fuzzing. In the test case generation stage, machine learning algorithm can optimize seed selection, guide mutation strategies, and facilitate the generation of high-quality test cases. In the input selection stage, involve filtering and prioritizing test input before execution, eliminating the invalid cases, and reducing computation time. Machine learning technique can also be applied to predict effectiveness and accessibility of test input. Finally, the result analysis stage, machine learning can effectively analyze numerous test data, identifying the true flaw within a large number of crashes and abnormalities. This automation reduces manual effort required for result analysis and improve the overall efficiency for fast testing. In pre-processing stage, machine learning algorithm can play a crucial role in analyzing and predicting the information obtained during the pre-processing. This enhances the effectiveness of program analysis technique combined with fuzzing. For example, Pangolin introduced the concept of incremental fuzzing, which involve a polyhedral path abstraction method to accelerate constraint solving in collaborative execution. Polyhedral path abstraction helps in summarizing program path in a more abstract and mathematical manner, making it easier to identify and prioritize paths that need further testing. This method significantly improves the efficiency and vulnerability discovered by focusing on the most critical paths. Other techniques like tank analysis can be integrated with machine learning algorithms to provide a more accurate and efficient pre-processing. Tank analysis tracks flow of user input through program to identify potential security risks. By leveraging machine learning in this stage, we can ensure that fuzzing process is better informed and more effective. Test generation stage. The test generation stage is where machine learning has significant impact. Machine learning algorithm can optimize seed selection, guide mutation strategies, and facilitate generation of high-quality test cases. For example, long short-term memory LSTM neural network can be used to learn the structure of input data and predict high-value seed for mutation. We shall propose a test case classification method based on LSTM neural network, where the test cases are passed through the LSTM and linear layer to obtain probability of input belonging to a certain class. This model trained using the test cases and a coverage stage, resulting in accurate prediction model for input categories. By prioritizing the mutation of higher value seed, the seed selection process is guided. Genetic algorithm is another powerful tool in test case generation. They simulate the natural process of gene recombination and evolution, enhance the ability test case to trigger exception. By performing selection, crossover, mutation operation on the test cases, genetic algorithm can generate diverse and high-quality test cases. For example, Sun, a protocol Fuzz called GA Fuzzer, can combine genetic algorithm with fuzzing. This model construct a dynamic fitness function, introduce dynamic notation and crossover probabilities, improving both the test hit rate and the test case coverage. Input selection stage. The input selection stage involves filtering and prioritizing test input before execution to eliminate invalid cases and reduce computation time. Machine learning techniques can be applied there to predict effectiveness and accessibility of test input, thereby improving efficiency of fuzzing. For example, Hu proposed a quasi-recurrent neural network-based fuzzing case filtering method for network protocols. This method, combined with preprocessing prediction capabilities of the QRM model for sequential data, effectively learning the structural feature of the neural network protocol and automatically filter invalid test cases. This has not only improved the efficiency of network protocol fuzzing, but also enhanced the quality of test cases that are executed. Another example is Fuzz, a directed gray box fuzzers that can predict the reachability of test input without executing target program. By learning from previous execution input, Fuzz can predict whether the program can execute the target error code with newly generated input. If the predicted result is unreachable, the input will not be executed, saving actual execution time and improving overall efficiency. Result analysis stage. In the result analysis stage, machine learning can be efficiently analyze the numerous test results, identifying true vulnerabilities within a large number of crashes and anomalies. This automation reduces manual effort required to result analyze and improve overall efficiency of fuzzing. For example, Harsh utilized 4 methods: supervised, unsupervised, supervised, plus supervised, and semi-supervised, with various techniques such as decision tree, support vector machine, mean clustering, and naive Bayes experimental address the root cause of the analysis problem. Given the lack of label data, Harsh proposed semi-supervised method that is best suited for most real-world scenarios. This method was evaluated on Eclipse software, demonstrating its flexibility and effectiveness in automating result analysis. By leveraging machine learning techniques at this stage, we can significantly enhance the accuracy and efficiency of the identifying and analysis vulnerabilities. Performance gains from machine learning in fuzzing. The integration of machine learning with fuzzing provides several performance gains, include increasing coverage, improving vulnerability detection capabilities, enhancing efficiency, and higher test case effectiveness. Coverage is one of the most important indicators for evaluating fuzz performance, as it reflects possibility of triggering crashes. Existing research has shown that machine learning algorithms applied in fuzzing can effectively improve the coverage and greatly enhance the ability to trigger crashes. For instance, MP-Fuzz improved coverage by a factor of 4 over conventional fuzzers, while SmartFuzz improved statement coverage by 2.8 to 3.4 and branch coverage by 20.7 to 26.9 in terms of vulnerability detection and capabilities. Machine learning-based fuzzer has demonstrated significantly improvement in detection vulnerabilities. For example, AMS Fuzz discovered average 226.2 bugs in Lava M dataset, exceeding previous unknown bugs in real programs. Efficiency is another critical metric, referring to the total number of coverage paths or the number of test cases that trigger program crash in the same amount of time. Studies have shown that machine learning-based fuzzer achieve higher efficiency compared to traditional fuzzer. For instance, Darwin is 488.26 hour than MOPT. The Comfort detect 158 unique vulnerabilities by automatically running 250 self-generated for 200 hours. Finally, test case effectively refer to rate which test case can effectively input into a target program. Representing the bypass capabilities, research has shown that machine learning-based fuzzer can achieve higher test case rate effectiveness, resulting in better performance in vulnerability detection. Challenges and future prospect. While integration of machine learning with fuzzing brings significantly benefit, outpercent in certain challenges. One of the main challenges is potential slowdown in fuzzing tests due to time-consuming and computational expensive nature of machine learning model training. To address this issue, researchers are exploring strategies to leverage parallel computing to enhance fuzz efficiency and effectiveness. In addition to address the challenges, future research should also be focused on expanding applications area of fuzzing as research on machine learning techniques grows. As an increased number of researchers are focused on applying machine learning model in fuzzing, it's important that standardized test days, the quality of test dataset, directly affect the training effect of the machine learning model and the performance of vulnerability detection model. Establishing standardized dataset for programs and vulnerability types in various fields will be meaningful for advancement of fuzzing research. Lastly, research should focus on expanding types of vulnerability detections. Traditional fuzz techniques often rely on program crash as an indication of detecting anomalies, but now our vulnerability resolving crash is therefore debuffing method to detect more types of vulnerabilities, including those triggered by multiple input points at different levels, can be researched in the future. In conclusion, the integration of machine learning technique with fuzzing offers significant advancements in vulnerability discovery and software security by addressing the limitation of traditional fuzzing method. Machine learning enhance coverage, vulnerability detection capabilities, efficiency, and test case effectiveness. The application of machine learning spans across various stages of fuzzing processing, including pre-processing, test case generation, input selection, and result analysis. However, it's important to address the challenges associated with this integration, such as potential slowdown due to model training and need for standardized dataset. Future research can focus on optimizing machine learning models and expanding the application area of fuzzing, and develop method to select a wider range of vulnerabilities. Continuous research and innovations in this field will further enhance the efficiency and effectiveness of fuzzing techniques. Hope this presentation has provided you with some understanding of machine learning-based fuzzing techniques and their potential to enhance vulnerability discovery. And here's the reference page.